Oxidation-reduction reactions. So we've been talking about different kinds of reactions. An oxidation-reduction reaction is a chemical reaction in which electrons are transferred. They're transferred from one reactant to another reactant. Now, oxidation-reduction is a long hyphenated word, so sometimes we shorten that to redox, which always makes me think of Redbox and makes me want to make some popcorn. But it's redox. So redox means oxidation reduction. So an example here is if we take a piece of zinc metal and put it in a solution containing copper ions, a chemical reaction will occur, just spontaneously all by itself. The zinc metal reacts with the copper ions to form zinc ions and copper metal. Now, how does a zinc atom become a zinc ion? It has to lose 2 electrons, right? That's how it gets the 2+ charge. Number of protons don't change, number of electrons can change. So the zinc atom has lost electrons. That's called being oxidized. Oxidation is losing electrons. How does a copper ion become a copper atom? By gaining 2 electrons. Where did those 2 electrons come from? They came from the zinc atom. Now, the question of why a zinc atom would give a copper ion 2 electrons, that's a whole other subject that we're not going to get into, but it happens. The copper ions are reduced. Reduction is gaining electrons. So what's happened in this reaction is that electrons have moved from one thing to another thing. In the acid-base neutralization reaction, it was a proton or a hydrogen ion that was getting shifted back and forth, right? So here it's electrons. Here's a picture. So here's a piece of zinc metal, and you stick it in this pretty blue solution of copper ions, and you can actually watch this happen. The surface of the zinc metal begins to change color. It's not going to look like a shiny penny, but it gets kind of pebbly looking and dark colored. And that's because what's happening is that the copper ions, as they're just moving around in the solution, will come in contact with the zinc metal. And when they do, this electron transfer takes place. And the zinc atom gives 2 electrons to a copper ion. And that copper ion becomes a copper atom. Copper atoms are not soluble in water. Copper metal does not dissolve in water. That's a good thing. Now this zinc ion is formed, and zinc ions are soluble in water, and so the zinc moves away. And so we're exchanging the zinc metal for copper, and that changes the appearance of the metal. Does that make sense? So it's an electron transfer. We can write half reactions to illustrate this. The oxidation and reduction are each a separate process, but they always occur together. So we'll sometimes write the reactions separately, and because it's half of the total reaction, we call them half reactions. So the reaction occurring with the zinc is that the zinc atom is losing 2 electrons. So zinc atom goes to a zinc ion plus 2 electrons. Those 2 electrons leave the zinc. And then we have the other reaction happening is the copper ion is getting 2 electrons to become a copper atom. Where did those 2 electrons come from? They came from the zinc reaction. So in order for this copper ion to gain 2 electrons, the electrons have to come from somewhere. There's no electron bank where you can go and just say, I need 2 electrons, please. There's no place like that. There's no electron shelter where if zinc wants to get rid of 2 electrons, you can say, hey, I don't want these 2 electrons anymore, here, you take them. Or where copper can go and adopt 2 electrons, like you could adopt 2 puppies or something. They have to come directly from another species. So they always happen together. If we take these 2 half reactions and add them together, we get the overall reaction. So I told you before that chemical equations are a little bit like math equations, except we have an arrow here instead of an equal sign. So let's look at what happens if we add. So we take these 2 equations, and we're going to add them together. Here's our reaction arrow. We need to keep everything on the correct side of the reaction arrow. It's not a very good reaction arrow. So what do we have over here? We have copper ion and zinc and 2 electrons. We've got zinc metal and copper ion and 2 electrons. But look, we've got 2 electrons over here also. We've got 2 electrons on this side and 2 electrons on that side. Those are a little bit like the spectator ions that we just crossed out. Because these 2 electrons that were produced from this half reaction get used up in this half reaction. And so we don't actually see anything going on with the electrons. So instead of writing the electrons in there, we cross those out. They essentially cancel out. And then in our products, we're going to have zinc 2+, aqueous, and copper solid. Yes?
Is this still considered a half reaction?
This is not a half reaction. This is the complete reaction. Each of these is a half reaction. So if you see a reaction, an equation that has electrons in it, it's technically a half reaction. Because it cannot occur by itself. This reaction cannot happen alone. There has to be some other reaction that uses those electrons. Because electrons can't just be thrown out or come from somewhere, just nowhere. They have to come from someone, okay? Any questions? Yeah.
And then also, if there's anything else that repeats, do we cross it out, or is it just the
You could have other things that would repeat. We're going to stick with really simple oxidation-reduction reactions, so that probably won't happen. But in Chem 1A, you'll do more complicated ones, and there will be things like water and hydroxide ions and things that'll cross out, just like the spectator ions did. So, like many things in chemistry, we have these 2 related things that we have to keep track of. We have oxidation and we have reduction. One is loss of electrons, one is gain of electrons. It's very easy to get them backwards. And so we need some sort of a memory trick to help us remember. So a common one is oil rig. So oil rig, and that stands for oxidation is loss, that's the oil. Oxidation is loss of electrons. Reduction is gain of electrons. And if you're doing work where you refer to oxidation and reduction all the time, then you would naturally remember it. I don't teach this very often. It's just, once a semester. And in between, my brain has other things to think about. And so I don't just bring this up immediately. I can't just look at something and say, oh, that's oxidation. I actually think oil rig in my head every time I look at one of those reactions. Oxidation is loss. Okay, then I can figure it out. So that's how I remember it, and I recommend that you do that the same way. So oxidation is loss of electrons, reduction is gain of electrons. And then, as if that isn't confusing enough, we have to have the agents. So let's talk about movie stars for a minute. So there's the movie star, and they have an agent, right? Who stars in the movies? The movie star or their agent? The movie star. What does the agent do? The agent helps them get the role in the movie, right? But the agent doesn't actually star in the movie. So we're using the word agent here in the same way. A reducing agent is not something that gets reduced. It's something that arranges for something else to be reduced. So a reducing agent causes another species to be reduced. An oxidizing agent causes another species to be oxidized. If this oxidizing agent is oxidizing something else, then itself it is being reduced. And that is just, I wish I didn't have to tell you about that, but that's what it is. So just think about movie stars and remember, oh no, it's backwards, okay? The reducing agent gets oxidized. The oxidizing agent gets reduced because the oxidizing agent arranges for something else to be oxidized. Well, how do we identify what's going on? What's being oxidized, what's being reduced? Well, when we're dealing with ionic compounds, it's fairly easy because we can just look at the charges. Just like the example we looked at with copper and zinc. We can see, oh, the zinc went from zinc atoms to zinc ions. How did that happen? It lost electrons. Is that oxidation or reduction? Loss of electrons. Oxidation is loss of electrons. So the zinc was oxidized. So let's look at this example. Write half reactions and identify what is being oxidized and what's being reduced. And then it's also asking us to identify what is the reducing agent. So what we're going to do here for this calcium oxide, that's an ionic compound, isn't it? So we're going to look at the individual ions. The ions that are present in there are calcium 2 plus and oxygen 2 minus. So one half reaction is going to be calcium going to calcium 2 plus, and the other is going to be O2 going to O2 minus. Now, we're not going to worry about phases in our half reactions. It doesn't matter. And what I'm teaching you here is just like baby steps in oxidation reduction reactions. So there's going to be a lot of stuff that you're like, oh, but what about this? We're just going to try to stay to the easy stuff. And I might accidentally assign a problem in the homework that's too hard, and I'll just apologize for that up front. We're not going to go very deep in this. So we're just going to look at the individual elements. So here's calcium, what it's starting with, what is it ending up as? Well, it's ending up as the ion. How does calcium go from being an atom to being an ion? It's about the electrons. And the charges can help us, because if we look at this equation, we can't have charges just changing. The overall total charge on both sides of the reaction arrow needs to be the same. So if I'm going to try to balance this, it's already mass balanced. There's one calcium atom and one calcium atom here. But this has a 2 plus charge. And so I've got a 0 charge on this side. I need to have the same charge on both sides. So the way I can take care of that is by adding 2 electrons over here. And if we think about it, that should make sense as well, because how would you make a calcium ion from a calcium atom? You'd have to take 2 electrons off of it to get the 2 plus charge. So you guys okay with this half reaction? And then here's oxygen, and here's O2 minus. We want to make sure that we've got the correct number of atoms first. Over here I have 2 oxygens, and over here I only have 1 oxygen. So what I need to do is I need to put a 2 here. because this O2 molecule is going to make two oxide ions, right? It's going to come apart, and then there's this thing going on with the electrons. So how could I get this to have the same charge on both sides of the arrow just by using electrons? What charge do I have on the left side? 0. And what total charge is on the right side? -4, right? Because each of these oxygen ions has a -2 charge, and there's 2 of them. So that tells me that this must have gained 4 electrons. So this is going to be 4 electrons plus that oxygen molecule is going to give me 2 oxide ions. We took the oxygen molecule and we broke the bond, we pulled them apart, and we stuck 2 electrons on each of the oxygens. And we made 2 oxide ions. Does that make sense? Now, if I add these together, am I going to get the overall reaction that's up on the top there? Are these 2 electrons going to cancel out with these 4 electrons? No. 1 calcium atom making a calcium ion gives us 2 electrons. But in order to react this oxygen molecule, I need 4 electrons. And then look at this. This has a coefficient on it, right? 2 calciums, and I end up with 2 calcium oxides. So I need to multiply this top equation by 2. I need to have 2 calciums, 2 calcium atoms making 2 calcium ions, and 4 electrons. So these 4 electrons then get used in this second half reaction to make the oxide ions. And if we were to add those together, we'd say, well, okay, the 4 electrons that were made get used up, so they're basically just not there. And then we would copy down the rest of what we've got here. We've got calcium, 2 calciums, and an oxygen molecule, and that's giving us 2 calcium ions and 2 oxide ions. And then hopefully we can recognize that these 2 calcium ions and 2 oxide ions could combine to make 2 calcium oxide formula units. We're not done with the problem, but do you have any questions yet? Okay, so we wrote the half reactions. We're supposed to identify what's being oxidized. We're looking at the reactants. We're not looking at the products when it's saying what's being oxidized, what's being reduced. We're starting with calcium, we're starting with oxygen. One of them's being oxidized, one's being reduced. So oxidation is loss of electrons, oil rig. Oxidation is loss, reduction is gain. So which one of these is losing electrons? Here's calcium going to calcium ions, and it's losing, those electrons are going away from it. They're leaving. So the calcium is being oxidized. What's being reduced? What's gaining electrons? The oxygen. So this is gaining the electrons. Oxygen plus 4 electrons gives us this, which is part of our product. So the O2 is being reduced. You're looking to see which of these reactants is losing electrons, which of them is gaining electrons. So we identified what's being oxidized, what's being reduced, what's the reducing agent. calcium is not being reduced, but it's causing oxygen to be reduced. It is the agent for change. It's the agent for reduction. So calcium is the reducing agent for oxygen. Oxygen is getting reduced. So calcium is the reducing agent. You're all sitting there in somewhat stunned silence. I'm not sure what that means. Any questions? Clear as mud? Can't even formulate a question?
Does that mean that oxygen is the oxidizing agent?
Yes, so oxygen would be the oxidizing agent.
Because oxygen is the oxidizing agent, are all redox reactions, do they always have oxygen in the reaction?
That's a good question. Many redox reactions have oxygen, but you do not have to have oxygen. And the term oxidized and oxidizing agent does come from oxygen's name. It was originally observed that this metal, calcium, is gaining oxygen. And whenever a metal reacts with oxygen, it is oxidized. And so it reacted with oxygen, it's oxidized. And then later, when we figured out what electrons are, then we realized what the real process was that was going on. But the name stuck, oxidized. So when a metal reacts with oxygen, it always loses electrons because metals form cations. And the only way something can react with oxygen is to lose electrons. Any other questions? So when we're dealing with ionic compounds, we can just look at the charges. But what if we don't have ionic compounds? What if we have elements and molecular compounds? There's no charges to look at. Does that mean there's no oxidation reduction? No, it doesn't. When we have molecular compounds, we get a partial transfer of electrons. In an ionic compound being formed, you have a complete transfer. But in a molecular compound, we get a partial transfer of electrons. That's a lot harder to observe. So because there aren't any ions and there's no charges, then we need some other way to keep track of, well, who's getting these partial electrons? And that thing that we need there is called an oxidation number. So oxidation numbers help us to identify what's being oxidized and reduced. The oxidation number is the charge an atom would have if electrons were transferred completely. So for the ionic compounds, those simple monatomic ions, the oxidation number is the same as the ionic charge. But in a molecular compound where there are no ions, the oxidation number helps us to identify what's being oxidized and what's being reduced. So how do we decide what the oxidation number is? There's basically 3 rules. Your book lists them as 2 rules, but I separated it into 3. So the first rule is that the oxidation number of any element in its elemental form is 0. That basically just establishes a starting point. So if you have oxygen in its molecular form, O2, its oxidation number is 0. If you have calcium metal, its oxidation number is 0. So any element, the oxidation number is 0. The oxidation number of a monatomic ion is equal to the charge on the ion. It's just the same thing. So there's nothing new to learn there. You know, sodium ion, we know from the periodic table its charge is +1. So the oxidation number would be +1. Oxidation numbers in any chemical species sum to the overall charge on the species. And really, you could take this one statement, and that really covers rules 1 and 2. Basically, the oxidation numbers have to add up to the overall charge on the species. So in a molecule, molecules don't have charges, right? Molecules don't have charges. The oxidation numbers of all the atoms in that molecule have to add up to 0. And if we have a polyatomic ion like nitrate or perchlorate or something, the oxidation numbers have to add up to the charge on that ion. And then the nonmetals. So the nonmetals in a molecule or in a polyatomic ion tend to have the oxidation number equal to the charge they would have if they were an ion. If we look at, let's maybe look at carbon dioxide. Is that an ionic compound? No. Carbon is a nonmetal, oxygen's a nonmetal. There are no ions in this compound. So if we react carbon dioxide with something else, how can we tell if the carbon's being oxidized or the oxygen's being oxidized? How can we figure that out? We assign oxidation numbers. So we look at the carbon and we look at the oxygen, and the way I think of it is they want to have the charge that they would have as a monatomic ion. So oxygen. If oxygen was a monatomic ion, we know from the periodic table it would have a -2 charge. So I think of oxygen as wanting to be -2. What would carbon be? Carbon, depending on how you think of it, you could say, well, maybe it wants to be -4, because that would follow a pattern. You know, we were starting at the noble gases and going 0, -1, -2, -3, -4. Or maybe it would want to be +4. But we can't look at this and say there are ions. So we have to figure out what to do. I'm actually going to change this example because I realize carbon's not a good example there. Let's make this be sulfur dioxide. So oxygen wants to be -2. What does sulfur want to be? Also -2. Well, that would give us -2 and 2 -2s. That would give us -6. That's not going to work. All of the oxidation numbers have to add up to 0. So who wins, sulfur or oxygen? Well, we've got a list here that tells us who gets first choice. So when you have to pick with the nonmetals, fluorine always wins. Next is hydrogen. Fluorine wants to be -1. So fluorine gets to be -1. Next is hydrogen. Hydrogen wants to be +1. Hydrogen beats everybody but fluorine. Next is oxygen. Oxygen wants to be -2. And then after those, it goes in priority of group 7, group 6, group 5. Personally, I don't have much trouble remembering 7, 6, 5. But I had a hard time with the FHO. And so I was trying to come up with a way to remember that, and I thought about noodles. Have you ever had pho? Vietnamese noodle soup. Yummy. There's all kinds of little restaurants around here that serve pho. Okay, so pho is spelled PHO. I know that's not the same as FHO, but it's close, right? So I think pho, 7, 6, 5. And then I want to go out for lunch. So we look here. There's no fluorine. There's no hydrogen, but there's oxygen. So oxygen gets to be -2. I'm going to do this down here. So oxygen gets to be -2. And this is a technique that your book uses. I'm going to try to copy. I haven't used it before. So right under the element, we're going to write its oxidation number. And then below that, we're going to show the total contribution. So we've got 2 oxygens, and they are each -2. So there's a total of -4 in the oxidation numbers there. I think your book uses circles and squares. And so these numbers down here have to add up to 0. So what do I need over here? +4. I need +4 in here. And then I look up here, I've got 1 sulfur, and I need to have a total of +4 in the oxidation number, so this one has to be +4. This is a lot like ionic charges, but there are no ions in this compound. So here, sulfur's not necessarily super happy about being an oxidation number of +4, but he's going to deal with it because oxygen's stronger or more important or cooler or however you want to think about it. Any questions? We'll do some examples. So let's practice. Assign oxidation numbers to each atom in the following species. So here we've got chromium, just chromium all by itself. What's the oxidation number? 0. This is an element. There is only chromium, another way to think of it, and overall it has a 0 charge. And so all the oxidation numbers within this thing have to add up to 0, and since there's only chromium, it's got to be 0. So the oxidation number on chromium is 0. How about chromium 3+ ion? This is an ion with a +3 charge. The oxidation number is equal to the charge because this is a monatomic ion. There's just the one atom in here, chromium. So this is going to be +3. And I'm not going to get on you about this at all, but charges are written with the sign after, and oxidation numbers are written with the sign before. So if it looks like I'm doing it backwards, I'm not. Okay, carbon tetrachloride, CCl4. There's no ions in this. This is a molecular compound, right? So I'm going to pull it out over here. And we've got CCl4. Here's the circles, and there's the squares like your book does. So we say Fe765. There's no fluorine, there's no hydrogen, there's no oxygen. Group 7 is next. Chlorine is in group 7. Chlorine beats carbon. What does chlorine want to be? What would it be as an ion? It would be -1, right? So the chlorine gets to be -1. And then we look at how many chlorines are there. There's 4 chlorines. They are each -1 oxidation number. So that's a total of -4. And this has to add up to 0 because that's the overall charge. So that means this box must be +4 so that the boxes add up to 0. This +4, I'm going to divide it among all the carbon atoms. Well, there's only 1 carbon atom, so it gets all of it. And it gets to be +4. So in carbon tetrachloride, the carbon is +4, and the chlorine is -1, the oxidation numbers. Any questions? Very much like looking at charges in an ionic compound. Just remember, these are not ionic charges. Okay, strontium sulfate. This is an ionic compound. Let's look at the 2 ions involved. I'm going to erase this. What are the 2 ions in strontium sulfate? Well, there's the first one, the metal, strontium, and then there's sulfate. We want to look at these separately. It's easier that way. What's the charge on strontium ion? 2+. It's in group 2A in the periodic table. So this is 2 plus. What's the charge on sulfate ion? 2 minus. So you should know that because you were supposed to memorize it, but you could also figure it out from the formula here. If you know that strontium's 2 plus and there's 1 sulfate, it must be minus 2. So we're going to do these separately. What's the oxidation number of strontium 2 plus? Plus 2. It's the same as its charge. So we don't have to do anything fancy there. Strontium is plus 2. But the sulfate, overall this has a negative 2 charge, and we've got sulfur and we've got oxygen, and they're competing to get what they want. They are both in group 6. They both want to be minus 2, but they can't both be minus 2 because there's 4 oxygens and 1 sulfur, and if they were all minus 2, the overall charge would be minus 10, and it isn't. I'm going to draw these boxes and squares. So we've got competition. We need to think about that order. Fa 765. Fluorine, hydrogen, oxygen, group 7, group 6, group 5. Well, there's no fluorine, there's no hydrogen, but we've got oxygen. Oxygen gets what it wants. Oxygen gets to be minus 2. That's the charge it would take if it was an ion. And we use this to figure out what sulfur must be. So each oxygen has an oxidation number of minus 2. There are 4 oxygens in this molecule, in this ion. So 4 times negative 2 is negative 8. Here, the numbers in these 2 boxes have to add up to what? Negative 2. When it was a molecule, like CCl4, where the overall charge was 0, they had to add up to 0. But this is a polyatomic ion, and so all the oxidation numbers have to add up to the overall charge, negative 2. So we need these to add up to negative 2. Well, what minus 8 equals negative 2? Plus 6. And there is absolutely no shame in using your calculator for something like that. The goal here is to get the answer right, not to be good at mental math. Well, again, I only have 1 sulfur, and I need a plus 6 oxidation number from all the sulfurs in this molecule. There's only 1, so it's got to be plus 6. So strontium is plus 1, the sulfur is plus 6, and the oxygen, each of them, is minus 2. If we look at them like this and say, well, there's 1 strontium and there's 1 sulfur, that adds up to plus 8, and 4 oxygens at minus 2 each adds up to minus 8, and overall that adds up to 0, which is the overall charge on this formula unit. What's the name of this guy? Nitrate. So let's look at nitrate. So we're going to do the boxes and circles for this one. Here again, we've got 2 nonmetals. They're competing. So we say Fa 765. Fluorine, nope. Hydrogen, nope. Oxygen, yep, there's oxygen. What does oxygen want? It wants to have an oxidation number that's the same as the charge it would have as a monatomic ion, negative 2. So each of those oxygens gets to have the oxidation number minus 2. There are 3 of them. 3 times negative 2 is negative 6. So these boxes have to add up to what in this case? Negative 1, the overall charge on the polyatomic ion. So the nitrogen must be plus 5, because 5 minus 6 is negative 1. And again, there's only 1 nitrogen, and so it gets to be, it's plus 5. If there were 2 nitrogens, we'd have to split the plus 5. and they'd each be 2.5. And you can't have a 2.5 charge, but you can have fractional oxidation numbers because they're made up. We're describing partial electron transfer. Yes?
Are you getting the -6 from the O3, so there's 3 of them and that's negative charge?
Yep. The -6 is coming from each of these oxygens having -2, and there's 3 of them. So 3 times -2 is -6. So down here, we would say that the nitrogen is +5, and the oxygen is -2. And you'll see that oxygen is almost always -2, unless it's O2, the element, and then it would be 0. Any questions? You know, it's been a rough morning when I start with the double gulp first thing in the morning. I tell myself it could be worse. It's not vodka, right? It's not meth or cocaine, right? So it's just caffeine. Caffeine's my friend. It's one of my favorite molecules. Okay, here's a question from your book. Determine the oxidation number of each atom in the following compounds and ion. There's 3 compounds and 1 ion. Well, same thing we were doing just now. So SO2. I accidentally did that one in the previous example. So let's change it up, and oh, I can make it look better than that. Oh, maybe not. I wish things in life were so easy to fix. Let's make it SO3, just to be different. So SO3, we got our circles and we've got our boxes. Not sure why they chose those, but I'm kind of liking them actually. Just like in the sulfate ion that we looked at, the sulfur and the oxygen, they both want to be -2. That's how I think about it. Because if you had sulfur ion, sulfide would be -2, oxygen ion, oxide would be -2. But they can't both have their way. Somebody has to give. And so we follow the rules, the order, FUS 765. So again, fluorine, nope. Hydrogen, nope. Oxygen, yes. Oxygen gets to be -2. There are 3 oxygens. They are each -2. And so overall, we have the contribution of -6 from oxygens. Here, what's in the boxes has to add up to what? 0. All the oxidation numbers in a polyatomic ion or a molecular compound have to add up to the overall charge, which is 0. So those are always easier than adding up to negative numbers. So this must be +6. Again, there's only one sulfur, and so it's +6. So sulfur is +6, oxygen is -2. Any questions? Next one. Nah. NaH. Nobody thought that was funny. That's okay. What kind of a compound is that? Ionic. We can tell it's ionic because we always look at the first element. The first element is sodium. Sodium's a metal. It's got a metal in it. It's an ionic compound. So let's look at the ionic charges here. So we've got sodium and we've got hydrogen. What does sodium have as its charge? +1. So then what must the hydrogen be? -1. I don't think we've seen that before, have we? What would we name this thing? Just following the rules, Hydrogen is a non-metal making a negative ion. How do we name that? Hydride. Right? We change the ending of hydrogen to "ide." So this would be sodium hydride. Whoops. Sodium hydride. So we're not going to use Fe765 here because we have two ions, and the oxidation number of a monatomic ion is the same as its charge. So the oxidation number for the sodium is +1, and for the hydrogen it's -1. So sodium is being a bully. Hydrogen is not real happy about being -1, but it's going to do it because sodium's bigger. So sodium is +1, and the hydrogen is -1. Any questions? Mm-hmm.
I'm still a little confused on how those are +1 and -1 and not those.
Okay, how did I get the +1 and -1? It's the charges, yeah.
Okay.
So the reason the oxidation numbers are +1 and -1 is that the charges on these ions are +1 and -1.
You don't have to do the whole circle and square.
We don't have to do the circle square thing because each of these ions just has one atom in it. You only do the circles and the squares if you have a molecule or if you have a polyatomic ion, like dichromate or something, Cr2O7 2-. Then we've got two things that we have to figure out. We know overall the charge is -2, so overall the oxidation numbers add up to -2, but we don't know how to divvy it up in between. But with a monatomic ion, it's just the same as the charge. Okay, carbonate. Okay, polyatomic ion, now we have to do the circles and squares. So CO3, 2-. And we say, okay, well, we've got two nonmetals here, Fe765. No fluorines, no hydrogens, but we have oxygen. So oxygen gets to be -2. And there's 3 oxygens, and so that's -6. And overall, the boxes have to add up to what this time? -2. So the other box is what? +4. Because +4 and -6 add up to -2. There's only one carbon, so all of this +4 has to come from that one carbon. The carbon's +4. So we say carbon is +4, oxygen is -2. Any questions? Oxygen shows up in a lot of these things, doesn't it? It's the most abundant element. Okay. One last example of this. N2O3. How would we name that? Dinitrogen trioxide. It's a molecular compound, 2 nonmetals. N2O3. So we need circles and boxes here. Nitrogen and oxygen. Fe765. Oxygen comes before group 5. So the oxygen gets to be -2. Oxygen gets what it wants a lot. And again, we have 3 oxygens. 3 times -2 is -6. The boxes have to add up to what? 0. The overall charge on the molecule, which is 0. So the other box must be +6. And now, finally, we have an example where it's not just 1 here. There's 2 nitrogens. Together, they have to be +6. So they're each going to be +3. You see how that works? If we talk about, pitching in money towards the restaurant meal or divvying up cookies or something, everybody gets it. But when we talk about oxidation numbers, part of your brain just like freaks out and rebels and says, I'm not going to think about it. Tell it to shut up and deal. So nitrogen is +3, and oxygen again is -2. Any questions? Okay, so balancing simple redox equations. We're just going to do the simple ones. You'll get to more complicated ones in Chem 1A. But at least you're going to have a clue about what's going on. Because even though you're probably going to forget this on Thursday afternoon, after the exam, it'll have been through your mind once. And so when you hear it again in Chem 1A, you'll go, oh, yeah, I've heard about that. I vaguely remember that. And it'll be a lot easier than the rest of them. They're like, what are you talking about? When we're balancing redox equations, we have to count electrons. You can have an equation that appears to be balanced because you've got the right number of atoms of each element, but it actually is not in terms of how the electrons are being transferred. And so we're not going to get into why that is or worry about that. We're just going to look at how we do it. It's important that the number of electrons lost by the species being oxidized are equal to the number being gained by the species being reduced. Because like I said, there's no shelter for electrons. And you can't just leave them on the side of the road. You have to give them to someone. So if one atom is losing electrons, there has to be another atom to take them. So we use what's called a half reaction method. We write the two half reactions and balance them, and then fix things up so that the numbers of electrons are equal. And then we add the two half reactions together. And that's going to give us a balanced overall reaction. This is going to work for the simple ones. There's a couple extra steps for the more complicated ones. We're not going to go there. So let's balance this redox reaction using the half reaction method. So the half reaction method says let's write the two half reactions. There's one for oxidation, there's one for reduction. We're going to end up with two elements. One's being oxidized, one's being reduced. And I don't care which order that you do them in. Personally, I like to start with the one that comes first. So I'm going to put aluminum here. And then I'm going to, okay, so aluminum started out like that with no charge. And then over here, what's the product? Well, it's the aluminum. Aluminum doesn't turn into copper. Aluminum turns into aluminum ions. And then the other half reaction is the other reactant, Cu2+, and that's changing into copper with no charge. Okay, so I took the one reaction and I took it apart into two pieces. And again, I'm not going to worry about the state symbols when I'm doing the half reactions. Our ultimate goal is this equation, and so when we write it all back together, we'll just copy down the state symbols. So I need to balance this half reaction. I've got a +3 charge on this side and a 0 charge on that side. All you can do when you balance these is you can change the number of atoms, but that's not going to help me with charges, and I've already got one aluminum and one aluminum, so changing that's not going to fix anything. But I can add electrons in. So electrons have negative charges, so I'm going to add electrons to this side. There's a +3 charge. I need to add 3 electrons. That's a pitiful 3. Now when I look at the charges, the overall charge on the left is 0, and the overall charge on the right is 0, because 3+ and 3- add up to 0. You okay with that? On the bottom, what do I need to do to balance that? I need 2 electrons, right? So if I put 2 electrons over here, 2 electrons plus this 2 positive charge, that adds up to 0, and this add up is 0. They don't have to be 0 They just have to be the same on each side of the arrow. So I balance them. What it says here in the directions is balance them so the number of electrons are equal. Are my numbers of electrons equal? No, they're not. I need to make them the same. So I'm going to multiply. If I multiply this by 2, I'll get 6. And if I multiply this by 3, I'll get 6. So I'm going to multiply the whole thing, the whole equation, times 2. And this whole equation times 3. So that's what I'm doing. Now I'm going to, maybe I'll just change color here. So I'm going to put the coefficients in. I'm going to multiply it out. So multiplying everything by 2, I'm going to get 2 aluminums and 2 aluminum ions, and I'm going to get 6 electrons. And I'm going to erase this stuff because I took care of it. Okay with that? That's still balanced, right? And then at the bottom here, I'm going to multiply everything by 3. Let's get rid of this stuff here. Times 3 would be 3 coppers and 3 copper ions. And 2 times 3 is 6. This is still balanced. 6 electrons and 3 times 2 plus, the charges add up to 0, and the charges add up to 0. I've got 3 coppers on that side, 3 coppers on that side. But now when I add these two equations together, this half reaction is giving off or losing 6 electrons, and this half reaction is taking up or gaining 6 electrons. So I don't have any electrons that are unaccounted for. So the 6 electrons and the 6 electrons, and then I'm just going to copy down the other things. So I've got 2 aluminum. I'm going to stick my state symbols back in now. Solid plus 3 copper ions, aqueous, to give 2 aluminum ions plus, not and, plus 3 copper atoms. When we look at this equation, we might say, oh, well, that's balanced. I've got 1 aluminum and 1 aluminum and 1 copper and 1 copper. But the charges aren't the same. This side is plus 2 and that side's plus 3. We can't have charges appearing and disappearing. So balancing that without using the half reaction method sometimes is pretty doable, and other times it will really make your head hurt. And so the half reaction method enables us to balance this with respect to charge by counting the electrons. Any questions? Let's do another example. Balance this redox reaction using the half reaction method. So I've got 2 things. I've got hydrogen and I've got chromium. So I'm going to write 2 half reactions, 1 for the hydrogen and 1 for the chromium. So I've got H plus and I've got Cr. They're both reacting to make something else. So the H plus is making H2. And the Cr is going to Cr2 plus. I need to make sure that the atoms are balanced, and then I look at the electrons, because we've got to take care of the big stuff first. The electrons are small. We can fit those in. Here I have 1 hydrogen, and here I have 2 hydrogens. And so I need 2 hydrogens over here to balance the atoms. And then I need to put some electrons in here, because on the right side I have a 0 charge, and on the left side I have a plus 2 charge. Each of these is +1, and so the overall +2. So I'm going to put my electrons on this side. Those 2 electrons plus 2 hydrogen ions will give me 0 charge and 0 charge. What do I need to do on the second half reaction?
Add 2 electrons on the product side.
Add 2 electrons on the product side. If I put 2 electrons over here, so I've already got 1 chromium and 1 chromium. This has a +2 charge. If I put 2 electrons in there, then those charges will add up to 0, and I've got 0 charge over there. And then we're going to look at it and see, is the number of electrons the same? And they are. Nice, we don't have to do any multiplying. Which of these things is being oxidized? Chromium or hydrogen ion? Chromium. Oxidation is loss of electrons. The chromium is losing electrons. The hydrogen ion is gaining electrons. So the hydrogen ion is being reduced. So when I add these together, I get 2H plus aqueous plus chromium solid to form H2 gas plus chromium ion aqueous. When I cancel those, cross those out. That's an example of one that if you just balanced it according to the numbers of atoms, it would have worked out fine. But they're not all that way. Any questions? So there's a little section in your book about activity series of metals. We're going to skip that. So I've left off part of the question here. We're just going to do the part that I think we need to know. Balance each equation and indicate which element is oxidized and which is reduced. So we need to predict the products here as well. Well, we should select a drawing tool. That would be helpful. What do we think might happen here? I pulled this out of the book, and I'm just really not liking it at all. Okay, I'm gonna change this, and I'm gonna say I'm gonna give you the products because I don't think it's fair. So there's our products. We're supposed to balance this and indicate which element is oxidized and which is reduced. Well, we could try balancing it without doing half reactions. Here I've got 1 chromium, and there I've got 1 chromium. Here I have 3 acetate ions, and here I have 2 acetate ions. So I would need to put a 2 here to make 6 acetate ions, and put a 3 over here to make 3 acetate ions. And now I screwed up the chromiums, so I'd need to put a 2 over here, 2 chromiums and 2 chromiums. And then I've got 3 lead ions, and I need 3 lead atoms over there. Let's look at the half reactions, though, and see what's going on here. This is an ionic compound, and that's an ionic compound, right? What are the ions in there? We've got C2H3O2, that's acetate with a -1 charge, and we've got a lead ion. What's the charge on the lead ion? +2. I can tell that because it's got 2 acetate ions. 2 of these guys would be a total of -2 charge, and so this must be +2. And then over here, again, I've got the acetate ion, but I've got 3 of them. So what's the charge on the chromium ion? 3+. So my half reactions would be chromium going to chromium 3+. So chromium going to chromium 3+. And what's the other one? The lead 2+ going to lead. Is anything really happening to the acetate? No, it's just kind of hanging around. It's actually a spectator ion in this process. So I've got lead 2+ going to lead with no charge. If I balance these half reactions, this is going to be +3 electrons, and this one's going to be +2 electrons. Now I can really see what's being oxidized and what's being reduced. Which one's being oxidized? Chromium. The chromium is losing electrons. So chromium is being oxidized, and the lead is being reduced. Lead is reduced. Chromium's an ox, and lead is red. And then let's just double check that this balance up here is correct. To balance these, we need to have them come up with the same number of electrons, right? So we'd multiply this one by 2, and we'd multiply this one by 3. And if I go ahead and carry that out, it's just a 2 and a 2, and that becomes a 6. And multiplying this one by 3, that becomes a 6, and a 3, and a 3. The 6 electrons would cross out. 2 chromiums, 3 leads. So I've got 2 chromiums and 3 leads. There's the acetates that didn't do anything. And there's 2 chromium ions with the acetates that didn't do anything, and the 3 leads. Any questions? Okay, I'm going to finish, I'm going to give you the products on this one as well. Products are going to be tin 4 iodide and hydrogen ion. So let's try balancing it just the regular way. What would we do? Are the tins balanced? SN and SN? Yes. How about the hydrogens? No. And the iodines aren't balanced either. So I've got four iodines over here. So I'm going to put a 4 here. And then I've got 4 hydrogens, and I only have 2 hydrogens over there, so I'm going to put a 2. Well, what would the 2 half reactions be? This is an acid, right? It's hydroiodic acid. It's dissolved in water. So, and it's a strong acid. It ionizes. And so that gives us hydrogen ion, an iodide ion. this is an ionic compound. That gives us tin and iodide, and the tin is 4+. And over here we have hydrogen. How could we identify what's being oxidized without doing half reactions?
It becomes an ion.
If it becomes an ion, yeah. So here we've got tin going from tin 0, no charge, to tin 4+. How does it do that? Does it lose electrons or gain electrons? It loses electrons, right? Oxidation is loss of electrons, so the tin is being oxidized because it's losing electrons. What's being reduced? Hydrogen. Is anything happening to the iodide? It's the same. The hydrogen's going from +1 to 0. It does that by gaining electrons. Reduction is gain of electrons. So the H+ is being reduced. Let's practice our oxidation numbers. What's the oxidation number for tin here? 0. How about for hydrogen? Yeah, +1. What if we didn't recognize that this ionizes and we just looked at HI? Then we'd have to say Fe765. Fluorine, hydrogen, hydrogen. Hydrogen gets to be +1. And what does the iodide have to be? It has to be -1. And then over here, tin and 4 iodines. This is an ionic compound, so we look at charges. The tin is +4, the iodine is -1. And in H2, what is the oxidation number for 0? I mean, for hydrogen? 0. What's the oxidation number for 0? 0? So tin is going from 0 to +4. The oxidation number is increasing. That's oxidation. Hydrogen is going from +1 to 0. Its oxidation number is being reduced. That's reduction. That should be enough to make you really dangerous.